My name is Michael Gattozzi, and today I want to bring you on a journey from what to no way that works to wait, why does that work? And then true understanding and acceptance. Many an article or talk has been created about idiomatic rust or proper code or whatever else the kids say these days. However, I've spent a long time gazing into the non-idiomatic abyss of the weird-exprs.rs test file. A file which contains the kinds of programs that are nonsensical Rust, but technically correct Rust. The best kind of correct. A file hidden deep in the bowels of the Rust compiler test suite, designed to protect against messing up parsing rules and testing weird edge cases that rustc must accept, even if we don't want it to. A test file known to the compiler devs as a necessary evil, sequestered from the public lest it make both old and new Rustaceans run away in abject horror. A test file that shows us just what kinds of wretched programs mortals are capable of inflicting upon the world. Come with me on a journey to truly understand this file by first understanding where and why it came into being. In the beginning, there was commit 664B0AD, made on August 19th, 2011. In it was a file titled weird-exprs.rs. This was a mistake that was not noticed for a few commits, and then renamed to weird-exprs.rs on September 26th, 2011. This file will be 11 years old in 2 weeks. It's been around for quite some time because no matter what point in time the language exists at, we have valid programs that we can write because of how the language is structured, that we wouldn't want to write, but we should still test for to make sure we don't break any edge cases and invariants. There are a lot of programs that rustc can accept and produce code for, but that we as programmers would find are not easy to read, helpful, or do anything we'd actually want a computer to do. This test suite has an equivalent analogy in the English sentence buffalo, 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 buffalo. It follows all the correct grammar of the language, however, it is nonsensical, but is also technically allowed. Weird-exprs.rs is the same thing. Here's one of those test cases from the file, and trust me when I say this is the least gnarly one to look at. It just prints Lincoln and assigns the unit type returned from println to evil. Sure, you can assign the unit value to a variable, but we wouldn't actually want to do that in the code we write. This is what I mean by valid but not helpful code. Now you might be wondering, why is it called evil Lincoln? Let's look at it in the original commit that added it. As you can see, println used to be called log, and for anyone not up to date on US presidential history, Lincoln lived in a log cabin he had built himself in Illinois back in the day. The name of the test has survived, but not the pre-1.0 syntax. Rust and what it looks like has both changed a lot and not a lot in the 11 years since this test was added. We use println, a macro, not log, a built-in keyword, and we assign with equals, not left arrow these days. Weird-exprs.rs has existed through most of Rust creation, and every step of the way since its inception, it has guarded the language from breaking its grammar and parsing rules. It was here before many of us started using Rust, and it will be here longer than many of us will be. Now that we understand just where this file came from, let's start looking into a few choice cases to learn a bit more about how Rust works, and let's get weird. If you look at the file today, you can see these allow pragmas, meaning we're going to have a good time because we're allowing ourselves to use the good code. Do note I can't cover every case with the time we have today, and so I have chosen the ones I think we can learn the most from. If you want to see all of the tests, which I really think you should, they're absolutely fascinating, will make you scratch your head for a bit as you figure them out, then I suggest reading them all here at source/test/ui/weirdexprs in the rustc repo at commit 491eb1. Let's talk about if. If lets you test some expression for a Boolean value of true, and if it's true, executes the block. In this case, we check it's true, and then execute the println macro. We could also have an optional else block that lets us do something in case it's false. In this case, we'd print, hello, I'm false. Did you know that if is an expression, though, in Rust, and not a statement? This means it's far more flexible and can be used in cases that expect an expression, such as variable assignment. This means you can test a condition and assign it a value depending on whether the condition is true or false, so long as the type in both blocks is the same. Did you know that the condition if accepts is also an expression? The only thing the condition must do is evaluate to a Boolean. In this case, we use an expression block, which will execute everything inside the block first. In this case, we print the sentence evaluating the expression block before evaluating and returning whatever the final value is without a semicolon, in this case true. Something to note about expression blocks is that they always return a type. It just defaults to the unit type if there is no type. Now let's talk about match for a second. It is also an expression that takes an expression. In this case, the value 1, which is a U8, and pattern matches on it. It tests the patterns in order of writing and then stops at the first one that matches the pattern, and then it executes the expression to the right of it. Rust forces you to match every possible pattern, and so we can use underscore as the catch-all pattern for every other number that a U8 can be. In this example, 1 matches on 1 and prints I am 1. We can go even further with match, as each pattern can accept an optional if guard alongside the pattern. Here we check the first pattern for x, and since it's the catch-all, we match and then ask if x is even. We see that it's not, and move on to the next pattern. We know the pattern will match, and then check is odd, which it is, since 1 is an odd number, and then print I am an odd number. Let's recap. If is an expression. If accepts expressions that it can evaluate to a Boolean. Match is an expression. Match patterns can have an optional if expression, and expressions that evaluate to a value can be assigned to a variable. Now you might be seeing where I'm going with this. If you can put in an expression inside an expression, and if is an expression, then you can get something like this test from weird-exprs.rs, which is designed to test that you can arbitrarily nest if expressions and that you can nest them in match expressions. So let's walk through what this test is doing. We first match on the unit type and go to the first pattern. We see the pattern is the unit type, and so now we need to check the nested if statements. We evaluate the first statement if true, and see we should use the if block, not the else block, which evaluates to true. We then use the true value from the first if as the input to the second if, which means we choose the if block, not the else block, which evaluates to true. We then evaluate the third if, and just like the previous two, we choose the if block and not the else block, which evaluates to true. Then we check if the last if is true for the match pattern, which it is, and so we choose that pattern in the match statement. We then assign the value true to the variable val. We then assert that val is true, which it is, and so the test passes. Let's kick things up a notch and talk about functions. We can define a function example with the above syntax, and when called, it will execute anything in the block. In this case, it will print out, I am a function. Okay, that's easy. Now we can also define functions for types like so. Here we have a struct bar that we impl a function example for that takes bar by value with the self argument, and then prints out, I am a function that takes bar as input. Now what if we change this so that it also returned a bar instead of printing out something? It would look like this, where the only difference is we're returning self, which is an alias for bar here, given we're inside an impl block. This would let us write some interesting code, because then we could call example as many times as we wanted, like this. We could keep chaining example here because we create a new bar in each call to example, and I promise this is going somewhere. I want to talk about function traits for a second. These let us pass functions and other functions generically. Here's what I mean. We define a function example that has a generic parameter f that is the type of the argument function. We restrict what f is with a where clause, saying that it must impl fn once, and that it takes no args and returns a string. We then define a body that will print out function string with the value of the function that we pass in that we invoke. In this case, foo and bar. We should note closures implement fn once, as do named functions. So let's recap. We can define functions that when called will execute what's inside the block. We can implement a function for a type that will take itself as the input. We can have a function return itself as a type, and we can therefore call a function over and over and over again. We also have a trait fn once that means whatever implements it can be invoked as a function that takes itself by value, and can have 0 or more arguments, and it can return a type. Now, fn once is a trait, right? Sure, closures and named functions inherently implement it, but shouldn't we be able to implement it for any type we want so that we can call it as a function? We can on Nightly Rust, and therefore in weird-exprs.rs, we do. First, we define a struct named foo inside of a function, which you can do. It limits it to only being created inside the function. A neat trick if you want to or need an intermediate type not to be exposed in the API. We then impl fn once for foo by saying it takes no args by using a tuple of size 0, and that its return type for the function call should be another type foo. We then define the function body where we return a new type foo after taking the old one by value with self and dropping it at the end of the function body. We then call foo, and much like before when we kept calling example, we just keep invoking foo as an fn once function, and eventually assign foo to the variable foo. This test is just making sure that yes, we can arbitrarily nest function calls one right after the other, so long as a function returns a function that you can call, which, yes, you can do so by just having a function return a function that impls fn, fn once, or fn mu. Now let's talk about loops in the never type. With loops, we have a loop keyword that will let us infinitely run the code inside the block. We can end a loop by using the break keyword. Now here's a neat thing. Loop is an expression, and so it can go wherever you want an expression. This means we can return a value from a loop like so. Here we return a value 5 from the loop by calling break and assign it to x. We then assert it's equal to 5. Now loops also have one other keyword, continue, which means stop evaluating this loop and start from the beginning. Here we print out stdout go brr, and then restart the loop again and never hit the unreachable statement. Okay, so we know a bit about loops, but what about that never type I mentioned? Never is an inbuilt primitive. Let's take a look at a quick example. Here the exclamation point is how we represent the never type. Since we return from the function early with the value 1, 2, 3, we can never assign it to x. Never is how we represent things that we can't construct or code we will never execute. Some control flow statements are this never type. Return is one, but so are continue and break, as they cause the code to stop where it is and jump to some other place. Another interesting thing is that these keywords that are never can type check to anything, as you will never need the type for that part. So, for example, this compiles just fine, as we exit the function early and can't assign any value to x no matter what type it is. Let's recap then. We have a loop keyword which loops infinitely. We can use break to exit a loop, or exit a loop and return a value. We can use continue to start at the beginning of a loop. Some control flow words like break and continue are what's known as the never type, and the never type checks as any type. With this, we're ready to look at our next case. For the sake of brevity, I'm just going to show you the control flow of this handy diagram. I'm kidding, but the important part here is that what this test is testing for, which is that break and continue can be used anywhere, and type check, while still letting the loop execute where it can. A bit nonsensical for control flow, but absolutely necessary. Now, let's talk about keywords. Rust has 3 types of keywords: reserved, strict, and weak. Reserved keywords are words that we might use in the future, but have no purpose for yet. They're reserved so that no one uses them in their code, which could cause it to break in later versions of the Rust compiler, where they become used for something. We also have strict keywords, which means these words cannot be used as a name of items, variables, function parameters, fields, variants, type parameters, lifetime parameters, loop labels, macros, attributes, macro placeholders, or crates. Words like loop, return, and fn fall into this category. We also have weak keywords. These are only special in certain contexts and so can be used in places you couldn't use strict keywords. Union, macro, rules, and tick static are the weak keywords. Din was also a weak keyword in 2015 edition, but was promoted to a strict one in 2018. Now, with all this in mind, what about primitives in Rust like U8? Is it not a strict keyword? My editor highlights U8 as well as other keywords, so certainly it's a special word. It's not. It's just an inbuilt type, which means we need to test that primitives can be used anywhere as a name you would not be able to for strict keywords, like so. This function is a bit hard to parse, but let me break it down for you. This function first checks that the argument input, which is a U8, named U8, is not equal to 0, which we are specifying is a U8 explicitly. We then assert that a value 8 of type U8 is equal to the return value of an expression block, which defines a macro U8 that takes the literal token U8 to define a module U8 with a function named U8 with a lifetime tick U8 that must outlive the lifetimes tick U8 and tick U8 with an argument U8 that's a ref tick U8 of a U8 that returns a ref tick U8 of type U8. In that function, it creates an ref static stir with the value U8 and returns the function argument U8. We then call the macro U8 with the argument U8, create a variable named ref U8 with type ref U8 to assign it ref 8 U8 as the value after calling the function U8 from the module U8, and then we call the original function U8 recursively with the value 0 U8, which hits the if statement and returns, and then return the value U8 from the block, which in this case is 8, since we pass in that value in the test case, meaning 8 is equal to 8. See, not hard to understand, just hard to parse. It's been a short yet dense journey that I've taken you on today. We've seen a lot, maybe too much for mortal eyes, and I sincerely apologize for showing you even a fraction of the weird-exprs.rs test file. But I hope you see the necessary evil that this file is in order to have the language we have today. I hope you go forth to read the rest of the file and just write more weird code. It's fun, even if it isn't useful. And you can learn a thing or two about Rust you didn't even know was possible, especially now that you know about weird expressions and where to find them. Thank you for your time.